Hello, in this Larch Environment video we're going to take another look at the worksheet system. We'll start by opening a document once again, this time a document called Compiler Demo Full. It has a single page called Compiler Worksheet, and this worksheet is somewhat more substantial than the one seen in the cellular automata demo seen previously. It's not animated and it's not as pretty, but it better demonstrates the capabilities of the system. I've also employed rich text far more in this worksheet to document the source code as I've gone through it. The first code block of interest is this one here, which defines an abstract base class called Node. It's the root of a hierarchy of classes which defines some AST nodes for our compiler. Node defines a present method, which means it can have a visual representation, as seen down here. It also delegates some of its responsibility to the present contents method. AST nodes present their class name followed by a colon, followed by whatever is created by present contents. In this case, a hidden node, some hidden content, so nothing. Now we move on to an integer literal class, which presents its value. And now we move on to a binary operator abstract class from which the add and null classes are defined. And here we can see that binary operators stack their operands vertically to the right of their class names. And I think this partially demonstrates the power of visual representations within Larch. This shows the tree structure of the AST much better than this textual representation here. Alright, now I move on to the parser. The parser uses Larch's Bright Fury parsing library and a simple grammar system that allows us to define grammar rules as methods within a class. This is based on the work of Alessandro Worth in his project called Ometa for Squeak Smalltalk, and you can find it if you have a look at the Viewpoints Research Institute website where his work is described. Here we see our parser is created. We have a test string, and we parse the string using our expression rule, and the result is shown here. We see our abstract syntax tree node, and we see it's embedded within a parse result structure that shows the fact that it was successful and that it consumed all of the characters. Now we need to turn our AST into something, preferably something a bit like assembly. So we define a class for representing a single instruction, shown here and visually represented. Now we define a class for representing an assembly program, a sequence of instructions. An example is shown here. Now we need a code generator to take an AST and convert it into instructions. We use our dispatch system, which, dependent on the class of the node that it's given, will select a method and invoke it. And this takes this AST constructed here and generates instructions that are placed inside this program here using the code generator created here, resulting in the program shown here. Now I want to execute the instructions, so we define a simple interactive virtual machine, and this simulates a very simple CPU. It has a program, an instruction pointer, some registers and a stack. And also it defines a present method, which means it can be presented visually, as seen here. We see our program, we see the state of the registers, and the state of the stack, which is currently empty because we haven't started executing yet. And we can step through the program and see the effect on the registers and the stack. This demonstrates that objects within Larch can not only have visual representations, but interactive visual representations. And these representations may include controls that alter the state of the underlying object that they're displaying. Now we move on to building a final compiler. We have a simple text editor box here for editing the expression that we're going to compile. This simply spits back the input that we gave it. We have our parse trace, courtesy of GraphViz, as seen in the Visual Console video. We have our AST that was generated as a result of the parsing, our assembly program, our interactive virtual machine, and our final result. When we step through the program, we see that the result ends up in this as the final entry in the stack. We can change the input by going back out to our text entry box and hold down Control and hit Enter to commit the changes. Our input changes there. We have a different parse trace graph. We have a different AST, a longer program, shown here in the VM, which creates a different result, shown here. That concludes this second worksheet video. Thank you very much for watching. Bye.